And we can start with a brief introduction of our speakers. Firstly, we have Dr. Maria Llanos Lopez Gonzalez from the Agronomy and Innovation Department of Agrisat in Spain. She's a biologist from the University of Alicante and PhD in Agricultural Science and Engineering from University of Castilla-La Mancha in Spain. She also has experience in plant physiological measurements in the field and using remote sensing, including chlorophyll fluorescence measurements at ground and airborne level. She has worked in the remote sensing and GIS group in the Centre National de la Recherche Scientifique, together with Laboratoire de Météorologie Dynamique. She has participated in different national and international projects, including TUdi, Startgate, Rexus, Lenses, and more, related with crops, water, soil fertilization, climate smart and precision agriculture, digital tools, water energy, food nexus solutions, and she has experience with close collaborations with different users and stakeholders. And next we have Dr. Zhudong Zhang, who is an associate professor from the Faculty of Geographical Science in Beijing Normal University. He received his bachelor's and master's degrees from Beijing Normal University and was awarded his PhD degree in soil science in the University of Potsdam, Germany. After that, he started to work in the Beijing Normal University. He is mainly engaged in the research and teaching of soil erosion, soil and water conservation, and soil geography. He is the director of the Institute of Physical Geography in the School of Geography. In recent years, he has undertook more than 10 projects, including National Nature Science Foundation of China and the National Key Research and Development Program of China. He has published 63 papers, including 32 international journal papers. His research covers water erosion, wind erosion, gully erosion, and the interactions among them. He is currently a visiting scientist in the Cardiff University in the UK. So once again, thank you for being a part of our workshop, and thank you for taking the time to be our speakers today. Llanos, maybe we can start with your presentation if you don't mind. You're
Okay, I will
muted here.
search my screen. I will put in a presentation mode. Okay, did you see the screen of the presentation mode?
We see the presentation mode.
So I need to change it. Is that?
Yeah, you need to change it.
Now it's okay?
Yes, that's fine.
No, perfect. So the first, thank you to invite me to these early career research workshops. So, okay, I'm Maria Llanos, as said, Nikolai said, and I would like to present the remote sensing for crop water and fertilization management. So we start. Okay. So I would like to present this slide because it's more or less our idea of our work is how we can connect the heaven with the earth, but in more technical things, we can say how to connect in the research and technology with the farmers. And for us, the technology is only a tool because we are a technology-based company, of course, but we understand the technology, the way how we can translate all this information and this technology, how to make available to the farmers and technicians, but in an easy way. So for us, the agriculture is the first because we are an agronomic enterprise. And this company was born among people who work in the field. I mean, the first people that funded Agrisat was researchers, but farmers and technicians. So the idea is to translate this technology from the farmers, from the researchers in the university, how we can translate all this technology, how this knowledge in a simple and practical tools for the agricultural management. So is this how the idea from AgriSat for the beginning? So this slide represents key moments in our history. So the background from AgriSat comes 20 years ago from the remote sensing and GIS group in the University of Castilla-La Mancha. So they use the images from satellites from Landsat. So at the beginning, these images you need to pay for to obtain this kind of information. With this information, the ERMOD project in 1997 starts to calibrate this kind of information from satellite from the users in the river basin authorities. So they translate the images from remote sensing in information for the water management in an area. After several years, we have two key moments. One is when the Landsat 8 images were free. So people can download these images and work with this free. So this is a key point because after that, the access to the technology and to the images were easier for the people and for the researcher groups. And the second key point was when the images from Sentinel-2 were free. So now we have images from everywhere to analyze and to obtain. The problems with that is that not all people has the knowledge to download these images, to trade this, calculate the NDVIs or another indexes. So the work of AgriSat is to translate this technology in a simple way for the farmers. So for this, we use, for example, the several projects that you can see there. So we translate all the information and all the knowledge from these projects to easy tools for the farmers. So all this knowledge, we can translate it in these services we can set, and I will present some of them in this presentation. We start with the crop monitoring using remote sensing. So I don't know if the people now in the audience knows something about the remote sensing. I hope yes. If not, I will present a very slide summarizing some concepts. So when the sunlight sits in several surfaces, the light reflected is different. So each surface absorbs and reflects light differently. So for example, in a white surface, the light is reflected. You can see that they reflect all the wavelengths of the kinds of lights, look to say like that. And the black surface not reflect light. So between these both extreme ranges, we have all the surfaces in the earth, we can see like that. So when the sunlight insists on the leaves, on the plants, on another surface, the light reflected is characteristics of this surface. So we can translate this in this graphic. So as you can see, the green vegetation has a different reflectance from the soil and from the water. So measurement this kind of differences between the reflectances for the surfaces, we can analyze what the sensor is seeing. In our case, we use the Sentinel-2 data because they're accessible for everywhere and with a pixel size of 10 per 10 meters. So we use two bands to calculate the NDVI. The NDVI is a vegetation index that represents the size and photosynthetic capacity of the vegetations. It's calculated using two bands, one in the red band of the visibles and the other with the near infrared band of Sentinel-2. So with this formula, we can calculate the NDVI using this reflectance in each surface, and we can obtain a signal spectrum of its surface. So for example, the NDVI reference value are, for example, with the bare soil around 0.15 and the maximum green vegetation covers until 0.91. So now we have more or less a little bit knowledge about what the NDVI represents. So we can translate this information is in this, how this example. So with Sentinel-2, we have more or less a sensor every 10 meters. So we use this information to analyze the surface for vegetation, soil, etc. This is an example how looks Spain with Sentinel-2 images. We can make more zoom to see the RGB composition, to see how looks the images. From these images, we can calculate the NDVI, the vegetation index, looks like this, and we can make more zoom to the parcels and to the field, and we can see the differences of NDVI inside of the parcels. So we can see the spatial distribution of this NDVI in our interest area of interest. So this is the basic knowledge that we use in our daily work. Another straightforward about the Sentinel-2 NV satellites is the time resolutions. The revisiting frequency for each single Sentinel-2 satellite is 10 days. So we have one image in 10 days. But now we have a combined constellation with both satellites, so we can have one image each 5 days. That means that we can follow the crop development during all the season. So how we can translate this information about the NDVI to the crop growing? So this is an example, this graphic to the right part of the screen. How, for example, this is a wheat. This is the different status and stage of the development of the wheats. So we can see how this, the vegetative part with the setting, emerging, tillering, left flag, etc. So how we can translate this? If we click in your left part of the screen, if we click here in the signal, we can obtain from this pixel the signature of NDVI. And we can obtain this graphic. Each point, each red point in this graphics means one value of NDVI per day. So the satellites pass through this area, we obtain the NDVI value and we can translate it and we can obtain a time series in this area. But this NDVI curves, how means related with the crop growing? So is that. So each point of NDVI translate the information about the crop growing. And each crop has their own signature. So for example, if we know the crop growing development and the dates where it's growing this crop, we can determine it with this curve. Is a wheat, is a poppy crop, is a purple garlic, is a corn, or we are onion, etc. So you can identify the crops by NDVI curves. So this is a summarize about what is the crop monitoring with the remote sensing. So we have the visualization and consulting of crop monitoring with RGB or NDVI. We have the NDVI time series, so we can differentiate the crop growth cycles. We can detect the management effects. So if you apply more or less fertilizer, or if you have problems in the development of your crop. And for example, these last images represent the area affected by animals. In this case, was in this area with rabbits. So they destroyed, the damage this area. So you can calculate the area affected for several reasons. And you can classify the crops in your area. So after that, you have your crop monitoring, but now we can obtain another information from these images. We can calculate the crop water requirements from your crops. In this case, we use the FAO 56 methodology, when you calculate the crop evapotranspiration, multiplying the crop coefficient per reference evapotranspiration. The reference evapotranspiration is calculated from radiation, temperature, wind speed, climate data from a reference surface, alfalfa of Stuka. And we have this information, we can obtain the forecast for 7 days. So this is one part. And the second part from this crop evapotranspiration is the crop coefficient. The crop coefficient, you can calculate it between the relationship with the NDVI. So depending of the crop, you can obtain different relationships. These different relationships are related with the percentage of the surface covered by the crops and the bare soil. For example, in goody crops, there are more bare soil compared with the vegetation cover. In herbaceous crop, like maize or wheat, the soil cover is quickly covered by the plants. So you can find a canopy completely covered by the plants. So these differences are these relationships. And how we can present this crop evapotranspiration to the farmers like this, like a simple way. We calculate these crop water requirements for a forecast from 7 days with the ATO, and we can obtain this map from each parcel has their own crop water requirements. So we present this very simple to say, okay, farmer, the next 7 days, your crop's water requirements is 21 millimeters for example. So this is how we can translate the remote sensing information to the farmers. This is our last case, the study. So the people can divide the pivot in different sectors and to analyze the water requirements in each sector separately. So this is very precision agriculture. But not only this information can use it for a parcel or for a farm. We can use this for a larger scales. So with the Sentinel-2 time series, with information of irrigate land use, the meteo data and soil types, we can make a soil water balance based on remote sensing to obtain this kind of maps. We can make the crop classification and estimate the crop water requirements, for example, in a river basin area. But not only we can use the remote sensing for irrigation, we can use it to calculate several indices for fertilization management. In this case, I would like to present the nitrogen nutrition index. So is the ratio between the actual nitrogen concentrations over the critical nitrogen concentrations for the crop analysis. So we can we can calculate the different factors from different remote sensing data. In this case, the marine terrestrial chlorophyll index. The biomass can be calculated from the transpiration accumulated by remote sensing too. So we obtain these relationships and we calculate the nitrogen nutrition index. And what is the result? Is that. So we obtain this result from all the crops. But the problem with this is not a problem, it's an approach, is crop dependent. This is an example. For example, this is a pivot where is a sector was management the different way, and the values of NNI below 1, that means that there are under fertilization. Around 1.1 or 0.9, that means that you have in optimum nitrogen fertilization. And if you have over 1, that means that you have nitrogen enough to cover the crop needed requirements. And this we can translate it in a time series too. So we can, you see that you have 2 points in this sector. One is represented for the deficient nitrogen band, and the other is in the other part without the optimum nitrogen. So during the crop cycle, you can see your nitrogen requirements. This information can be translated together with NDVI, for example, in a nutrient balance, where you need to introduce several data. For example, the NDVI curve, the soil data, soil texture, nitrogen, initial nitrogen in your soils, or the phenology of your crops. And with this information, you can calculate this nitrogen balance. The gray line is the nitrogen mineralization in the soil. That means this gray line needs to be during the crop growing season over the dashed line that you can see in the screen. I don't know if you can see, but well. So if you calculate this balance, you can play with the application of the fertilizers in red columns, and you can see the behavior of the nitrogen in the soil. So changing the dates where the application and the amount of fertilizer, you can see if the gray line is over the dashed line or not. So you can say, you can obtain this soil nutrient balance in your soil for pre-season, and you can change it and adapting during the season in a real time, with real time. And with all this information, we can obtain another kind of product or the management in your areas. It is the management soil maps. So with the NDVI time series, we calculate the transpiration accumulated per pixel. We can obtain the changes according to the parcel average. You obtain the average transpiration accumulated in the area, and each pixel is related with these changes. So you obtain this map of intraparcel variability, where if your data are around 100, means that you are in the median, in the average of the parcels. Is it less, you have in the less productive potential, you have less productive potential in this area. And if you are over 100, that means that your area has more productive potential. So this is an example how the behavior of the crop in these different areas is representative of the area. So you can classify your area in different productive potential zones. This information, what can you use this information? You can select the soil sample location, for example. You can apply different fertilization strategies depending on the area of your parcels, different treatments or management, and you can include a different seed dose for your crop. An example how we can present this information to the farmers. You can obtain this management zone maps from different years with different crops, and you can see if in the same area you have a pattern. For example, in this in the right image in the maps, you can see that always the border of the boundary has a less productive area that in the center of the parcel. So with this information of the management zone maps, we can translate this into a variable rate fertilization. We can translate the variability in different rates of fertilizers. So this allows us to develop an appropriate variable dose application maps. We can estimate the potential saving from variable rates applications, and we can propose a strategy like that. So if you have an area with high production potential, you can apply higher dose of fertilizer because this area permits to uptake more fertilizer. And in the areas with less production potential, you apply lower dose, because if you apply the same in the same parcel and this area doesn't takes the nitrogen or the fertilizer enough to grow at the same at the higher areas, means that something happened in this area that doesn't permit that the plants take the fertilizers. This is, I don't know if you can see the video. This is a real case of variable rate fertilization. So it's possible to translate this information in a machine like that. So I'm finalizing, so I would like to add some remarks about that. So obviously, the remote sensing data have some limitation. For example, the free images has pixels in the case of Sentinel-2, pixels, the pixel size of 10 per 10 meters. So it's not enough maybe for parcels with surfaces less than 1,000 square meters. If you want high resolution images, you need to pay for them. Some problems with the cloudy areas, because in the case of NDVI, are very affected for the clouds. And if you want to create a map needs to have some knowledge about this. But the another pros is that you can have any image from anywhere of the world with other extensions. The temporal frequency is the 5 and 10 days, so we have images in real time from the developed crop. Now is the reduced cost because it are free. The only thing that you need to pay, maybe is, for example, in our case, is the platform to see these images. And you can go through the past because there are a stock of images from the past. And my last slide is that the remote sensing is a key tool for precision agriculture that allow to crop monitoring, the crop classification, the crop water requirements estimation, not only a plot, but basin level, the detection of irrigated lands. We can calculate and estimate an irrigation scheduling and fertilization scheduling. We can quantify the damages in accidents in the crop development. We can analyze a diagnosis of the status of the fertilizations. We can calculate from these maps the potential productivity and the yield we can estimate, and we can have a forecast harvest. I would like to include that this information is improved if you use drones. They have some lags and some pros regarding with the satellite, but all the information that you can use for the agriculture management is welcome always. So thank you very much for your attention.
So I can issue messages of everyday life are products of the land. So
Thank you very much, Janos. That was a really great presentation. Does anyone have any questions in regards to this session? Yes, Gunther?
Yes, thank you, Janos. It was very interesting. I'm wondering, where does it make sense to apply this, to use remote sensing? I mean, it has a lot of benefits, but does it only make sense if you do irrigation and have a minimum size of parcels, or could it be interesting for small structured agriculture like in Austria or in China, for example? Who are your normal customers? Are they also small farmers, or are they more big associations?
No, our customers are different sizes parcels. For example, we work with people with rain-fed crops and with irrigated crops. So the technology you can apply in everywhere in this all kind of crops, because obviously the irrigation crops, irrigation services, you cannot apply this on rain-fed crops, but the fertilization, yes, the crop monitoring, yes. And for example, we are working with an insurance company, so you can analyze the damage of the droughts, frost, or every event, to analyze what are the effects in your yield estimated crop, for example. So this can be useful in rain-fed crops. And with the size of the parcels, yes, it's a lack of the remote sensing, but we were working with small plots for example, in Valencia. In Valencia, there are very small crops of orange trees. So it depends of the size of your parcels and the shape of your parcels. We can use remote sensing or not. This is true.
Okay.
Yeah.
And maybe another thing. So it is mainly applied for water management and also fertilization. Are there some special applications for soil quality related issues, or I guess it's quite closely related to fertilization management, that you get information about the soil quality related to the needed fertilization and NDVI.
What? I'm not sure that. What do you mean?
Do you also get some specific information about soil quality from remote data?
Yes,
Or
finally, the NDVI represents how the crop is growing. So if you have a problem in your soil, these changes in your soil is reflected in how the crop is growing in your area. So this is because it's the one thing that you can use the remote sensing. When I talk about the management zone maps, these changes in the area means that something happened in the soil. So you can go to take the soil samples in the different areas. So this is one thing that you can use the NDVI, for example, to say if you have difference in your soil. And another thing is the NNI, for example, the nitrogen nutrition index. That means that if you have enough nitrogen in your soil and the plants can take it, you have a high values of this index. If not, is the lot. So if your plants that don't take this nitrogen, so something happen in your soil. There are more indexes related with the soil characteristics in the soil filters, but we are more related with the crops, not in the soil in this case.
Thank you very much.
No, you're welcome.
Do we have any other questions, or can we move on to our next session? Okay, thank you very much, Janos. Once again, it was a great session. I hope you stay for our next one as well. Dr. Zhang, it's your turn now. Hello. You are muted, sorry. Yep.
Yeah. Hi, hello, Nikolai. Yeah, thank you for your hosting. Okay, I share my presentation. So, can you see the presentation?
Yep.
Okay. So good morning and good afternoon, dear colleagues. Pleasure to introduce my work on gully erosion in this workshop. So My talk is about gully erosion in agriculture and pastoral landscapes. So first, I would like to give some background of gully erosion. So, gully is an erosion gully with a certain width and depth passed by ordinary agricultural farming machineries. In other definitions, for example, by Paulson, refers to an erosion gully with a cross-section of area greater than about 1 square meter. So in the field of erosion, we can see different types. So there are real, ephemeral gully and gully. So from real to gully, it means the erosion intensity increases. So gully erosion is a quite severe status of soil erosion. And the soil erosion, the gully erosion can causes a lot of consequences. For example, it gets the agricultural land loss and also the reduced food production and seriously influence the sediments in the rivers, and even in some cases, the gullies can endanger the houses. You can see in the pictures. And to study the gully erosion, scientists applied different approaches. For example, we can use the measurement by differential GPS to measure the morphology of the gully and its development. And in larger scales, we can use the remote sensing or UAV and the GIS to monitor and identify the gully shapes and the development. And based on this, scientists also apply mathematical simulation to simulate the development of gullies. And among these approaches, the differential GPS measurement is a reliable and precise approach to determine the volume change of the gully development. Because for example, the frequently used remote sensing techniques, in most cases, they can only identify the area of the gullies, but it's difficult to identify the depth and further the volume of the gullies. And some UAV can have a higher precision and can get the elevation data, but in some gullies they're often covered with vegetations, so there are also uncertainties by the UAV method. So in my talk today, I introduce some two case studies using the differential GPS measurement for gully erosion studies. So the gullies distribute all over the world. You can see this is a well-known review paper published in 2016. So most areas of the world has the gullies. And in my studies, I have these two study areas. You can see one is in the northeast part of China. It's the black soil region of China. And the other one is in the North China, close to Beijing. And these two areas you can see in the black soil regions, these gullies, and also in the near Beijing, we have these gully erosions. So the black soil region, it's in a more agricultural landscapes. There are many cultivated lands. It's an important grain production area of China. And the other one is more grassland and is used for the pastures. Let's first see the black soil region case. In this area, the topography is the undulating terrain with very long slope lengths and quite a small slope gradient. And the average slope gradient is about 1 to 3 degrees. And the climate here is a cool, temperate, continental, subhumid, and with average annual temperature about 0 and annual precipitation about 500 millimeters. And most of the precipitation occurs between July to September. So to determine the gully erosion rates, we used the RTK GPS measurement. In 2018, we applied the high precision differential GPS to measure 7 typical gullies and also made detailed field investigations. And based on this data, we can use the GIS software to create the digital elevation model and I can then identify the parameters of the gully, such as the length, width, and ratio of width to length, also the depth and the cross-sectional area and the volume of the gullies. But when we want to determine the gully erosion, we need at least 2 measurements of 2 different times. So in this area, we have some legacy data from my colleagues from Wu 2008 and Dong 2019. They had such a measurement in these gullies from 2002 to 2005 and 2010. So this data can be used to compare with my measurement. Then the gully erosion can be identified. And based on this data, we can further analyze what factors influences the gully development in these areas. So these are some pictures of our work. We made a field investigation and RTK-GPS measurements. And also we used remote sensing images to interpret the gully development. And so in this area, we have measured 7 gullies. You can see these 7 gullies, most are distributed in one small watershed, and it's a typical watershed in the northeast black soil region. We can see that there are the gullies are distributed most in cultivated lands, and some also connect to the grassland and windbreaks, and has connection to the unpaved road, the agricultural road. Yeah, we have this field surveys, and here we can see one example of one big gully we interpreted from the remote sensing images from 2006 to 2017. We can obviously see the development of this gully, which is longer and wider, especially the gully head cut. You can see in the north at the top. Yeah, the head cut develops a lot. Yeah, from one gully head cut, yeah, it develops even into 2 head cuts. And another example is the gully 82. The gully head cut retreated 40 meters in these years, and the area increased from 3,600 square meters to 4,600. Yeah, and the volumes increased from 3,000 cubic meters to 4,000. So the area increased by more than 1/3, and the volume increased also about 1/3 this gully. So for this all 7 gullies, we can use the GIS analysis to identify their erosion amounts, and more important, we can identify the erosion spatial pattern, the distribution of the erosions. And besides the erosion, there are also some deposition occurred in the gullies. So this is a good benefits for applying the GPS, RTK GPS. We can get these results very in great details. And yeah, you can see the spatial pattern of the gullies. So you can see on the left, so the gullies, yeah, there are erosion segments, and also there are some deposition segments. Yeah, and yeah, these are examples of two gullies. And we can get the detailed statistics of this gully development. You can see among these seven gullies, yeah, there are 4 gullies have obvious headcut retreat, yeah, and the amount is considerable, and yeah, the volumes change, yeah. So here we can see some more analysis. So yeah, as I mentioned, my colleagues, they did this research in 2005, and they established some gully development models, yeah, that can predict the volume of these gullies over time. And you can see by these 3 gullies, we can see that, yeah, the gully 4 and the gully Fengshan have very good agreement of, yeah, between the prediction and our measurement. But for the gully 6, yeah, the difference is quite large. So this gully 6, the model is this middle picture figure. You can see, because, yeah, this, you can see that because this model was exponential equation. So yeah, this is quite I would say is risky for the modelers, yeah, because the erosion will not increase exponentially. Yeah, so this is why there are so much difference. And yeah, and for these 2 stages, from 2002 to 2005, the average annual retreating of gully headcut was 8.4 meters, and the average soil loss is between 300 to 2,000 tons per year. But in the next stages, from 2005 to 2018, yeah, the headcut retreat is only 3.4. Yeah, it's decreased a lot, and also the average annual loss also reduced to 16.4 to 600 tons per year. So that means the total erosion intensity showed a decreasing trend. So based on this data, we further analyze the factors influencing the gully development. So we analyzed in 3 perspectives: the topographical factor, including the drainage area, slope gradient, yeah, and the second one is the land use types. Yeah, as I mentioned, there are different land use types connecting to the gullies: cultivated land, grassland, road, yeah, and we also analyzed certain soil and water conservation measures, including the check dams and conventional forest. So the check dam is a kind of engineering measure, and the conservation of forest, we call it a biological measure for controlling gully erosion. So yeah, we can see that in the same small watershed, you can see the gully 2 and the gully 8 we can see that, yeah, the catchment area of the gully 2 is about 33 hectares, and the area for the gully 8 is about 150 hectares. And yeah, the comparison is very, very distinct, that the larger the catchment area, the larger gully erosion occurs. And yeah, from the table we can see the comparisons. Yeah, so you can see the aerial change ratio. Yeah, it's quite different. Yeah, one is 3% and the other is 27%. And the gully slope gradient has also great influence on the gully development. We can see that, yeah, these are the slope gradients of these 7 gullies. We can see that as the gradient increases, the volume change ratio increases accordingly. Yeah, yeah. This is the average slope of the whole gullies. And also we investigated the internal gradient in 2 gullies. Yes, gully 2-1 and gully 8-1. We can see that, yeah, in the different parts of one gully, yeah, the gully erosion rates also increases obviously with the slopes. And yeah, for example, in the Fengshan Gully, we can see that, yeah, you can see the gully headcut, yeah, has the largest slope, yeah, and the erosion is more obvious, yeah, and also in the lower reaches of the gully, yeah, have the similar trends. But we can also see some different phenomena. For example, in this gully, in the area from 120 to 240, these segments, you can see the slope gradient is more than 3. It's relatively more steeper parts of the gully, but the gully erosion is not so severe. Yeah, so from this case, we can see that the gully erosion is influenced by topography, but also influenced by other factors. For example, the vegetation. You can see in this part there are the green dots means there are conservational trees or small forests. You can see in this part, although the slope gradient is large, but the erosion is not obvious. And so this refers to the influence of the land use. So as I mentioned before, there are different land use types, and so we can see how the gully develops among these different land uses. We can see that, yeah, there is also erosion in the undisturbed grassland, the gully erosion. But in these gullies, the sediment accumulated in the grassland, and the volume of the gully even decreased. You can see the ratio is minus 32%. So this means deposition. Yeah, but yeah, for the gullies in the cultivated land, there is a large gully headcut retreat, and combined with the side erosion, the down cutting the gully volumes increases to a certain extent. You can see the Fengshan Gully and the 8-2 gullies. the volume increased significantly. Yeah, between 30% to 40%. And there are even more serious gully erosion in the gullies connecting to the road. Yeah, the agricultural roads. We can see that the gully erosion in this land use is more serious. Even there is no head cut retreat, but the volume increased a lot. This is because the road is compacted by the traffic, and there is very little infiltration on the road. So more runoff goes to the gullies nearby, and the gully erosion is quite severe there. And the other factor is we consider is the conservational measures. You can see that on the left and the right, there are different types of conservational measures. So the left, we can see this is a check dam. It's an engineering measure, and on the right there is the conservation forests, yeah, the biological measures. You can see these are the examples for the gullies with the check dams, and we can see that the gullies with the check dams experience significant volume changes. Yeah. So at the beginning, I think the check dam can conserve the soils and sediments in the gully, but yeah, because of the climate type, there are heavy precipitation or even storms in the summer, and the runoffs, the concentrated flows can in some cases the check dams is or the check dam itself or the check dams around the areas around the check dams can be destroyed by this concentrated floods, and the check dams some of the check dams have been washed away and exacerbated the lateral erosion and led to more severe down cutting of the gullies. Yeah, it acts as a similar to the waterfall, and you can see that for the gully 2-1 with the check dams, you can see that the green one is the cross section of 2005, and the black line is the topography of the 2018. We can see, yeah, the lateral erosion, yeah, it's about 2 meters. It's very heavy erosion here, and we can see for the gully 8-1 with the check dams, we can see that, yeah, the purple line is we measured in 2018. We can see that, yeah, in the lower reach of the check dams, after we can see, yeah, the depth increased 2 meters. Yeah, okay, this shows the great erosion there. Yeah, and the other measure is the conservation forest. We can see that the gully 8-2, yeah, with the conservation forest, we can see that except for the head cut retreat, the other parts of the gully were, yeah, well protected by the conservation trees, and the development of these parts almost stopped. Yeah, but for the gully 8-1, which has not the conservation forest, yeah, the volume increased even about 30 times. So this shows the great effect of the conservation trees. And the other gully, the gully 4, we can see that in the lower reaches of this gully, there are also the conservation forest, and this part becomes stable. Only the center area of this gully continues to widen and get deeper. And yeah, and the other gully, the gully 4, without these conservation trees, yeah, the aerial change rate is much higher. It's much higher. And yeah, in this gully Fengshan I mentioned before, we can also see the distinct differences. For example, in the northern part, where there are the conservation trees, you can see the depth of the gully increased very little, only about 0.2 meters. But in the lower reach, yeah, without the conservation trees, yeah, the depth increased 1 meter. Okay, to have a summary, that in the black soil region, the growth rate of the gullies from 2005 to 2018 was smaller than that from 2002 to 2005. Yeah, the average annual headcount retreat is about 3.4 meters, and the annual erosion volume is about 40 to 460 cubic meters. Yeah, both of which decreased significantly comparing to the previous stage, but some gullies still developed. And the erosion rate of the gully varies among different land use types, and the road gully system developed the fastest, and followed by the cultivated land and the grassland gullies. And the gully with check dam is still developing rapidly with obvious lateral erosion and down cutting. And the conservation forest can effectively slow down the development of the gully and prevent the collapse and the cutting of the gully wall. Okay, this is the first case, the gully erosion in the northeast of China, and the second one is near Beijing. Yeah, this has a little bit different context. Yeah, the gully erosion is a global environment problem. Yeah, and normally scientists study the gully erosion in the perspective of water erosion. Yeah, it's a result of gully erosion. And in this case, the impact of wind erosion on gully is rarely considered. You can see in this map, so many gullies studied, very few of them has considered the influence of wind erosion. And actually, in the areas influenced by both wind and water erosion, yeah, the wind erosion also plays a role in the development of gully erosion. Yeah, for example, many gullies exist in the wind and water eroded areas in North China, and they are subject to the influence of wind erosion as well. You can see that this the gully erosion in the Bashang grassland. You can see there are obvious activities of the wind erosion. Here you can see the sand depositions inside the gullies. Yeah, and so we have this case study in the Bashang grassland. Is about 200 meters north to Beijing. Yeah, the Bashang area belongs to the Hebei province, and in this area of about 160 square meters, we have made the regional identification of gullies by remote sensing. We can see that there are more than 300 gullies distributed in this area, and the density is about 1.8 gullies per square kilometer. Yeah, so the density is quite high, and the gully area covers about 2% of the total area. Yeah, and yeah, but the gully influences not only the area of the gully itself, but yeah, it has much influence in the surrounding areas. And in this study, we also applied the RTK GPS to monitor the development of 6 gullies, and this will have more frequent measurements. We measure the gullies twice a year, one in May and one in October, one in October. So this means why we choose these two points to make the measurement, because we think that from May to October is the period of water erosion, and from October to the next May, yeah, is the season majorly influenced by wind erosion. So we can, by these two measurements every year, we can explore the dynamics of water erosion and wind erosion in the gullies. So you see, these are some pictures of me and my students, and so according to our measured results, we can see that all the gullies have the considerable development. Yeah, the average annual gully area change rate is about 11%, and the larger gullies, the lower change rates, and the gullies also have the headcut retreat. Yeah, for example, and the retreat is about 0.5 meters per year, and this rate is quite smaller than other studies. For example, the headcut in Loess Plateau, and also smaller than the headcut retreat in North China, as I mentioned in the previous case studies. This because this Bashan area, the major land cover is grassland. Yeah, so it's more stable, and the headcut retreat is considerably smaller. And here we can see that the gully width also increases gradually. Yeah, this shows the development of the gully, and the larger gully is, the lower change rate, and the gully depth increases obviously after the water erosion season. And but you can also see that the gully depths decrease slightly after the wind erosion season. So this is what we were excited to find. Also, before the study, we also expected these results. Yeah, this means during the wind erosion season, the gully erosion is small because there's no rain, and the gullies experience the influence from the wind erosion, majorly the aeolian sediment deposition in the inside the gullies, and resulting the volume decrease of the gullies. So, for example, for this typical gully 3, we can see that for these gullies, for these 6 gullies, we can all have this phenomenon. You can see that, yeah, the gully volume increase annually. You can see, yeah, this from every year, from May to October, yeah, during the water erosion season, we can see the area of the volume of the gully increase significantly, and the increase of the volume is about 4%. And you can see during the winter erosion season, yeah, the gully volume decrease due to the aeolian sand deposition, and it's about 2% of the volumes. Yeah, this is quite different findings compared to other gully erosion studies. And yeah, we can see the more aeolian sand deposition, the more sediment production and a higher sediment delivery ratio, higher SDR. Yeah, but the higher SDR does not really mean the more severe gully erosion. Yeah, because we have to consider that the net gully erosion, which means the total erosion minus the previous aeolian deposition in the gully. And according to our result, we can see that the more aeolian sand deposition, the less net gully erosion. So it means the aeolian sand deposition inside the gully have a kind of protective effects on the gullies. And so to summarize the process, we can see that the gullies in these wind and water eroded areas, the gully development, in April, in the autumn and the winter and the next spring, we can see that there are wind erosion caused the aeolian sediment deposition inside the gully. Yeah, and the volume decreases. And then in the next water erosion period, yeah, the water erosion erodes the gully and also the aeolian sands. Yeah, and then to the next circle. So according to our result that, yeah, the aeolian deposition inside the gully is about 2%, and the water erosion, yeah, is about 4%. So totally the net erosion is about 2%. So to summarize, the gully erosion is a common phenomenon in the North China, and the gullies in the Bashan area has a slower erosion rate than other regions. Yeah, because of the grassland, and there is 2% aeolian sand deposition during wind erosion season and 4% erosion during water erosion season. And the aeolian sand provides sediment materials for water erosion, and it also has a protective effect on the gully. And yeah, from these two case studies, we can conclude that water erosion intensity determines the erosion rate of the gullies, and the agricultural activities, including the cultivation and also the agricultural roads, accelerates the gully erosion. And in the areas influenced by wind erosion, it's necessary to consider the role of the aeolian processes on gully development. And to control the gully erosion, the biological environment measures like the conservation forest is more effective than engineering measures in controlling gully erosion. Okay, that's all for my presentation. Thank you very much for your comments. Thank you.
Thank you very much, Dr. Zhang. Does anyone have any questions in regards to the presentation? Yes, Gunther.
Yes, thank you very much also for this very interesting presentation. I'm wondering, you said, of course, the vegetation protection is the best way to control erosion, but nonetheless, you showed examples for dams in gullies, which had partly positive effects. So you showed some had positive effects and caused deposition, and others had negative effects and even worsened the situation. Do you have an idea when these technical measures are successful and where they should not be used?
Okay, thank you, Gunther, for your comments. Yes, the I showed the examples. You can see 6. Yeah, in some gullies, there were some conservational plans for controlling the gully erosion in the northeast of China. Yeah, the check dams, you can see in this gully 2-1, there are 5 check dams. You can see there, and you can see that most of these check dams were destroyed. Yeah, by the water. Yeah, because in the summer, yeah, in this area the precipitation of the whole year concentrated in the summer between July to September, and also in the northeast China, the topographic is typical with the very long slope lengths. Yeah, so the catchment area is quite large. So the much precipitation concentrated into the gullies, and yeah, with high energy, and so the check dam is often destroyed. So nowadays there are in this area they have applied some new techniques, and the check dams has no longer applied. Yeah, so nowadays they protect the whole gully walls, not to create the dams inside the gully. This was also, I think, some lessons from the failure of the check dams. Yeah.
And I have one more question.
Yes.
You have very intense measurements, but with a quite low temporal resolution. How do you distinguish between the effect of water erosion and wind erosion just by the area where erosion takes place, or also, do you also look at do they have different effects on the texture of the deposit soil? Or yeah, because I guess both water and wind erosion takes place within these periods between the measurements.
Okay.
You know.
So Gota, you mean in this northeast case, or only in the second case?
In the second case, where you showed that 2% are aeolian and 4% are.
Yes. So in the second case, yeah, it's true that the measurement frequency is not high. Yeah, twice a year. So this is how to say, it's a preliminary exploring of this potential effect of wind erosion in the development of the gullies. So we made, yeah, it's a simple assumption that we divide the year into two parts. Yeah, from May to October, we assume it's the period of water erosion, and the other is wind erosion. I think, yeah, from October to the next April, the precipitation is quite limited. Okay, the rainfall is quite limited.
Yeah.
But still there are, yeah, we didn't consider the other precipitation, the snow and the melting of the snow in spring. Yeah, there is also possible water erosion by the snow melting. Yeah. So this part we did not consider. Yeah. I think this is a very good point. We can to do some research in the next steps. Yeah.
Okay. Yeah. Everything clear. Thank you very much.
Yeah.
Thanks a lot.
Thank you. Thank you.
And we
Hello, Nicola. Hello,
Yeah.
Gangsa. Hello, Nicolette.
Hello.
Yes, sorry, my video doesn't work. Hello, Eunice. Yanis. Hello. Yeah,
Hello,
your
Sophie.
yeah, your topic is good. Is a good work, excellent work. Is interesting. My question or comments is for 卓栋's presentation. It is interesting for your work. For gully erosion, when you analyze, your work is to find what's the factor to influence gully development. I noticed that the check dam, the gully around the check dam developed quickly. It is very surprising to me. Another comment is for your presentation about the wind erosion and water erosion. I wanted to know what's the soil type of the basin that is such area. And didn't you find the phenomena about hyper concentrated sediment flow? Because on the Loess Plateau, on the north of the Loess Plateau, there's a lot of sandy area, Maosu sandland. There have a lot of phenomena about hyper concentrated sediment flow. That is another, or called by the scientists the third another erosion driven factor or force, erosion force. One is water, one is wind, another erosion force in that area. So the soil erosion modulus is super high there. Just because the phenomena about the hyper-concentrated sediment flow occurred there. So did you find the phenomena here in Basan area? Because there is wind erosion, a lot of the deposition there. Yes, that is my question. Hold on. The third question is, how long will you stay in London?
Okay. Thank you very much, Professor Zhang, for your comments and questions. Yeah, the first one is about the check dams. Yeah, you can see the pictures. Yeah, for example, this check dam, yeah, was destroyed by the flow. Yeah, I think Professor Zhang was surprised by this result of the check dams. Yeah, I think this the difference between the Northeast China and the Loess Plateau area. Yeah, as I mentioned, the Northeast China, yeah, it's a very long slope length and small slope gradient. So there are very large catchment area and can receive. I think the catchment, the drainage area, yeah, for the gully, I think is much larger than that in Loess Plateau. Yeah, because Loess Plateau is the slope is very steep. Yeah, and so with this very large drainage area, yeah, so much water can concentrate and it can destroy the check dams. And the next question is about the soil types of this in the Bashang area. You can see that the soils here are quite sandy, Yeah.
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 From the large spatial scale, the soil here is belongs to the area of the chestnut soil, according to the WRB. And yeah, but in this area, you can see, yeah, because of the heavy grazing in the past, yeah, the grassland degraded a lot, and yeah, the soil is characterized by very high sand content. So yeah, and Professor Zhang mentioned the high concentration
Concentrated.
concentrated.
高含沙水流.
Yeah, yeah,
Yeah.
yeah. I think this flow is exists in this area. Yeah, yeah. But in our study, we did not investigate this in situ during the water erosion events. Yeah, I think this is a very good suggestion that we can continue this research and make the on-site measurement and monitoring or to observe these high concentrated flows in this area. Yeah, and okay, the third question. Yeah, I will stay.
That's the question.
Yeah, I will stay in UK for 3 months. Yeah, and this is my first week here. Yeah, so
yeah.
so when we made the appointment of this dates, yeah, I think I also explained that, yeah, in the November 25th, I would be on the flight. Yeah, that's why I prefer the appointment today. Yeah.
Okay. Yeah. 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 So don't forget the
Yes,
commitment of ISWCR.
yeah. I'm working on that. Yeah.
Yeah. The submission time is 20
Yes.
December.
Yeah.
Okay. Yeah. Yeah. Yes, over here, over my yes, finish for me. Quickly, yeah.
Thank you.
Keep shouting. We also had one question in the chat from Ignacio, who asks, how do you measure the protective effect on the gullies of the deposition material derived for wind erosion?
Measure the protective effect of the gullies on the to protect. Okay. Yeah. I have one slide that you can see. So from this slide, we did such a figure to compare, yeah, the net erosion, yeah, the net gully erosion changes according to the proportion of the deposition of the deposition of the aeolian sand. Yeah, this figure shows, yeah, when the more aeolian sand deposition, yeah, the less gully erosion. I mean the net gully erosion. Yeah. So we think, yeah, how to explain the protective effect, yeah, because I think the erosive agent for the gully is majorly by the water. So when the water comes to the gully, yeah, it first have to erode away the sand deposited in the gully. So in this process, yeah, it will consume some energy of the flows. Yeah, this we consider the protective effect of the of the aeolian sand on the gully. Yeah. And you mean how to measure? We can in this case we only determine this amount by the change of the volumes of the gullies. So it's the 2% and 4%, and the overall net erosion is 2%. Yeah, maybe these values may vary inside the different parts of the gullies. Yeah, and this result is only the overall result. Yeah, for the whole gullies. Yeah.
Thank you very much. Does anyone else have any questions? I think there is no more questions. I'd like to thank everyone for attending today, and specifically our two speakers. Thank you very much. It was very, very interesting. And yeah, we will have at least one more early career researchers workshop next year. So we will keep you in the loop for that. And thank you once again, and have a nice day.
Thank you.
Thank you very
Thank
much.
you, you
Thank you
too,
very
and
much.
Hyun-sung. Thank you.
Yeah.
Bye.
Bye-bye.
Ciao.
Bye bye.
Bye bye.